This is the setup for the demonstration of the logic analyzer part of the digital discovery. The digital discovery is on the left, and on the right is a demonstration board manufactured by Rigol. It's outputting a 16-bit analog to digital signal. In other words, it's converting an analog signal into a 16-bit value. And then those 16 bits are being brought over to the digital inputs of the analog discovery. Now, for those of you that may be a little bit ahead of the class on this one, I am not using the high-speed adapter or the high-speed cables on this, because the first thing I want to do is determine what the limits are using the supplied flywire cables. As you'll see later when we talk about the high-speed adapter, it comes with some special cables, but it is a $50 optional add-on. So we'd like to find out how good the digital inputs are without that additional adapter. Over on the screen is the display, and we'll talk more about that a little later as well. Currently, I'm running this at 200 megahertz, you see over there, which gives us 1 microsecond per division. And at the very bottom, you see the highest speed output. That is running at essentially 12.5 megahertz because it's the first output. And of course, as you probably know, a D to A converter, the clock speed, in this case it's 25 megahertz, the data is only output every clock, so each transition represents half a cycle. So the highest speed that you can get on the output is 12 of a 25 megahertz A to D is 12.5 megahertz. In other words, 2 samples at a 25 megahertz rate. So before we delve into the details of this and look at the performance, what I would like to do is give you a little bit of an overview of the logic analyzer part of the digital discovery. In this section, we've been using the input dividers, which are the 24 high-speed data inputs. Now, when I say high speed, the speed varies depending on whether you use the high-speed adapter, which we'll talk about in a second. But the output of the dividers goes to bank 1 of the Spartan FPGA. Bank 1 then controls the data that gets written to the data memory. Now, the data memory is the place out of which you display the results. So basically, the data flow is from the input pins through the dividers into bank 1 of the FPGA, where various things are done, including creating the appropriate triggers and so on. And then the data is stored in the data memory. Now, as we talked about in the overview, the rest of this is primarily associated with the management of the FPGA, and the heart of this digital discovery is this fairly high-speed FPGA. When I say fairly, there are of course faster ones, but for an instrument of this class, basically $200, this is a pretty fast FPGA. And that's one of the reasons why you can get such high performance out of it. It is a faster FPGA than the one that's used in the analog discovery. So now let's look at the inputs, dividers, and the high-speed adapter. Here is the circuit that's used for each data input. In other words, this is repeated 24 times. The data in comes through a 51K resistor shunted by 120 picofarads into a node which has a 510K resistor to the reference voltage. Now the reason for the reference voltage is so that you can adjust the threshold level of the input. In other words, if you're using, say, 3.3 volt logic, then you probably want the threshold to be around 1.4 volts. But if you're using 2 volt logic, you want the threshold to be around 1 volt. In other words, roughly half of your supply voltage. Now the particulars of that I'll leave to the user because it varies from one family, logic family to another. Then there is a clamp diode that goes to the 3.3 volt VCC, designed to prevent the output from exceeding the 3.3 volt limits of this FPGA. Now I point out that the digital discovery will work with 5 volt signals. In fact, it will tolerate up to 20 volts plus and minus on this input. But the largest logic level that it will reliably work with is 5 volts. So it will work with TTL and TTL CMOS logic. It will not work with higher voltage logic. That exceeds its capabilities, and you would have to use some kind of input divider circuit, which is, of course, completely separate from the digital discovery. The reason I point that out is, of course, don't try to use this in a 12 volt logic circuit, for example, or anything like that. It's just not made for that. It's made for, at most, 5 volts input. And frankly, it's optimized for the low voltage CMOS, in other words, 3.3 volts and below. Now let's take a look at the high-speed divider, but before we do, I commend to you to look at the input resistor and the 510K. Now, at high frequencies, these resistors, of course, are shunted by stray capacitance, and in the case of the 51K, by this 120 picofarad capacitor here, which we will talk about in a second. But essentially, at low frequencies, the input impedance of this network is about 560K. Now, the high-speed adapter for the logic analyzer works with a group of these cables. I'll show you one in just a second. On one end is a 2-pin connector where the 2 pins are fused together. And that is the end that is supposed to be attached to the high-speed adapter. I'll show you that in a second. The other end of the cables are the ends that are supposed to be connected to your logic. And those are the ends that contain this 100 ohm resistor. Now, some people have asked, what's the purpose of that 100 ohm resistor? And the purpose is to isolate the capacitance of the cable. In other words, it works very similar to the way a 10x probe on an oscilloscope works. A 10x probe on an oscilloscope, you have generally a 1 meg input impedance. You put a 9 meg resistor at the probe tip, and that isolates the signal from the capacity, in that case, of a coaxial cable. In this case, we're using a twisted pair, and the twisted pair is used to maintain relatively constant impedance from one end of this cable to the other. So now let's take a look at that actual hardware. Here is the high-speed adapter, and what I have done is plugged in one of these twisted pair cables. You may notice, I'll try to get it so that the camera will show it, that the ground wire goes to the top. This entire top row is ground of these pins. The bottom row is the signal pin. So for example, in this position, you have one of the high-speed data inputs. If you move this, say, over to this position. Now you still have the ground connected to this bus, but now you're using a different signal input. Now this high-speed adapter is designed to maintain the impedance match, and it plugs into the digital discovery in place of this flywire connector. In other words, it plugs in here. We aren't going to be using the high-speed adapter for this, although at some point I am going to test the performance of the high-speed adapter. But for right now, let's return to the experiment that we are conducting using the Rigol demonstration board and the analog to digital signals. We're back now to the waveforms display, and what I'm going to do is I'm going to advance the speed to the highest speed that this is capable of, which is 10 nanoseconds per division. You notice now that we are getting the actual transitions of this logic. Now, at the top is data in 15 and at the bottom is data in 0. I'm only using 16 of the available 24. Now, if you were doing this on the analog discovery, not the digital discovery, this would be your limit, 16 bits. Let's go to a slightly slower speed, 50 nanoseconds per division. And you start to see the power of this instrument. It really does do a pretty good job of locking to these signals. Now, this is basically an A2D that is counting down from 32,000 or 32K to 0. You may notice at the top here, it is decoding that as 32, this is 759, this is 764, and so on. This is 765, 766, and so on. So this is basically the ramp up portion of the analog to digital conversion cycle. Now what I'm going to do is continue to reduce the time. I'm going to go to 10 microseconds per division. You may notice now these highest speed inputs are basically grayed out, or they're so close together that they're essentially black. The first one that you can actually see the transitions on is DN2. Now, of course, this is not a limitation. This is simply the fact that when you're trying to display such a wide dynamic range of digital data, that you're rather forced to do this. Now, I have this now set so that the entire screen width is basically the cycle of the A2D converter. That is, there's 10 microseconds. In 10 microseconds, data in 15 goes through an entire transition. This is the falling edge, this is the rising edge, and then there's another falling edge here. Data in 14 is the next one down, and so on. Now, what I'm going to now do is zero in on the top line, which is more or less the control line, and discuss a little bit of what we have here. The first thing is the mode. In this case, we're using repeated mode. You can also use a shift mode, which, in other words, the data will shift across the screen. You can use a screen mode. In other words, it will fill one screen and then fill another screen and then fill another screen. And finally, you can record the data with the record mode. In other words, it transfers the data to a buffer that you can play back after you stopped the digital discovery. I right now have the trigger on normal. You can also use auto, trigger, or none. The source is the digital source, in other words, the digital inputs. You can use the patterns. Now, patterns, of course, means the pattern generator, which we will talk about in a separate section. And finally, a manual trigger source. So we are triggering on data in 15, and you see it over here. The T column is the trigger column. You may notice that there are X's below, but there is a rising edge symbol on this data in 15. So this is what we are triggering on. Now you change that by clicking up here on trigger on the T, and you can change that to whatever you would like. Right now we are using simple trigger. We could also use pulse trigger or trigger we're using a protocol. The inputs we are using are the 200 megahertz data in 0 through 24. Now, of course, we're only connected to 0 through 15. The position is simply the position relative to the trigger, and you have all of these choices. We're using the default samples, but we could actually just tell the unit how many samples to take. And finally, this is the relative speed that we are using at the present time. Now, the relative speed depends on the sample rate, or the let's now change this to 1 microsecond per division, and then let's go back over, and you see now it says we're running at 200 megahertz. So the last thing I would like to do before I close out this section is look at how the FPGA apportions the clock cycles depending on how many inputs you're using and what the kind of capture you're using. Here are the options available for, in essence, apportioning the clock cycles. You can get up to 800 megahertz of effective sampling. And you get an effective sampling rate of 256 megasamples. If you use 16 inputs like we were using in this example, the max you can get is 400 megahertz. Once again, remember, this depends on the display length. The longer the display length, the lower the frequency that you can use. So for a very short display length, you can get 400 megahertz. If you use the entire 24 bits, you are going to get a 200 megahertz sample rate. Now you may ask, well, why? I looked at the specs of the analog discovery and it says 100 megahertz. Why does it say 200 megahertz here? Well, remember the Nyquist criterion. To sample a signal, you need at least 2 samples per cycle. So at 100 megahertz, you have to have a 200 megahertz sample rate to maintain a 100 megahertz input signal. Now, the last thing that I want to mention is the noise option. If you turn on the noise option, you will notice that, as it says, having the noise option checked, half of the buffer is used for storing noise marks. So that effectively halves your sample rate. Digilant has chosen to oversample, so which is a good thing if you have the speed. So the reason that they're able, or that they are using 800 megahertz effective sample rate, is so they get essentially 4 samples per cycle with noise turned on. If you turn off the noise marks, you can get up to 800 megasamples per second of signal. But then, of course, you won't be able to see the noise spikes. I've changed the configuration. The digital discovery is now connected to the I2C bus simulator of the Rigol demo board, and I'd like to show you how you can add buses like I2C, SPI, and so on to the logic analyzer. Here is the logic analyzer with an I2C bus added. I hope you can read this on the camera. Up here it says I2C, and I'll show you how you add those in a second. The clock is set to data N0 and the data to data N1. Now, these are often called SCL and SDA on the modules that use this protocol. And at the top up here, you see the decoded bus output. The first symbol is, well, first is basically just the command to start receiving the data. The only thing that changes from one to the next on this simulator, that is the Rigol demo board, is this first byte. After that, it just spells out the letters Rigol, R-I-G-O-L, in ASCII. Now, these are hex, but in ASCII, that would spell Rigol. As you see, the capture begins with a falling data in line, and you see I have it set to trigger on a falling data in line. Now the actual trigger is over here. This is the preceding string. This is the actual string that was captured from that trigger. So, but they're basically the same string, and the reason I have the camera pointed over here is I want to show you how you go about adding buses like this. You click on the plus, and it gives you these options. That is a signal bus. You can simply define that as, for example, suppose you have just a straight 8-bit ASCII bus or a 4-bit hex bus or something like that. A bus, the difference between bus and signal is signal treats each line separately. A bus groups the lines together. So, for example, if you set up a 4-pin bus and you are using hex decoding, then the decoding up here will be the hex decoding of all 4 of those signals, and they'll all be treated together. This, of course, is a SPI bus, an I2C bus. UART is what is often called RS-232, and I'm not going to go into a lot of these because I've done this before with respect to the Analog Discovery 2, and essentially, since it uses the same software, they're basically the same. The difference is that the digital Discovery can run at higher speeds because it has the high-speed interface. Also, it can use a wider number of inputs, and it can use the I/O pins simultaneously without taking up any of the input pins. So in other words, you can have up to 16 I/O pins and still maintain 24-pin datum in monitoring. I2S, I point this out because this is not the same as I2C. Then one wire is a protocol that is used a lot with very simple modules. And finally, custom. Now, once you've added the bus, and I've already done that here, I added an I2C bus, you have to set up the data in and data out pins, and you do that at the time you add the bus. Then you have to make sure that you set up an adequate buffer. In this case, I'm just buffering 100. It could be a lot larger or smaller than that, depending on the particular requirements and the length of a transfer. Then you run, and if the patterns are completely stable, you'll get stable results. The problem is if the patterns are not completely repeated each time, you get this kind of a result. So you have to stop. This is the same problem you have with an oscilloscope with a bus decoder. And you see this time it stopped with an hex 65 here, and then went through the RIGOL sequence again. So this is the way that the logic analyzer decodes buses. It can be very, very useful, but as I pointed out a minute ago, I've done this before with regard to the analog discovery too, and except for the speed and bus width of the digital discovery, everything else is the same because it uses the same waveforms software. By the way, I'm using the latest version of waveforms. Earlier versions of waveforms did not have all of these buses. For example, the CAN bus. And the CAN bus is very, very useful, particularly if you are using the PMODs that Digilant sells for their chip kit processors. The reason is that the CAN is basically the connection protocol that is used in that system. If you're using the Digilant system, or it's actually in combination with the National Instruments software and other things, then you probably already know this. So I'm going to close off the logic analyzer review at this point, except that I do want to do a segment on the speed of the logic analyzer. But to do that, I'm going to have to set up a different arrangement and use a different signal source than the Rigol bus. So I'll break off here, and then I'll get to the next segment in just a few seconds. This is a 1 megahertz square wave with an occasional glitch. Let's run this out to the limits of the scope, which is 1 nanosecond per division. This is a 500 megahertz scope. And you notice that there is an occasional, I hope you can see that. Zoom in a little better, and maybe you can. You see the occasional short pulse. In other words, instead of rising and staying at the proper level, occasionally it mistriggers. Now, by mistrigger, the scope is not mistriggering, the signal is falling. It rises, and about 2 nanoseconds later it falls again. So this is a very tricky signal generally to work with. So let's see how the digital discovery handles it. Here is the screen of the digital discovery, and you notice that this is the basic signal, the basic 1 megahertz signal. Now what I'm going to do is go over here and use the pulse trigger option. And I'm going to use 10 nanoseconds. In other words, I want a positive pulse that is less than 10 nanoseconds. Remember, ours is only about 2 nanoseconds at the top and about 8 nanoseconds away from 0. So click on this. And you notice right there, it's catching that signal. Now let's go out to the limits, the horizontal limits of the unit, and you see it is actually catching that pulse, which is a pulse that's only, depending on where you measure it, but if you measure it from the 10% point on the rise to the 10% point on the fall, in other words, back to within 10% of ground, you get about 5 nanoseconds. So it's about a 5 nanosecond wide pulse. and the analog or digital discovery is handling that. Now let's take another quick look at how that's hooked up. The digital discovery is hooked up using the high-speed interface and one of these high-speed cables directly over to the board that's producing this anomalous signal. Now, I do not have equipment reliable enough for me to actually measure the sample rate of the digital discovery, the 800 megasamples per second. But it certainly looks like, given that it will pretty accurately reproduce a 5 nanosecond pulse width, that this is certainly adequate for virtually any digital applications that you're likely to encounter in a teaching lab. Now, obviously, there might be some really difficult situations under circumstances where you might require a better instrument than this, but that puts you into a price class that's way out of the digital discovery range. At any rate, I'm very impressed by the performance of this unit. Something that I may do at some point in the future, or perhaps a viewer might want to do this, is perform a similar kind of experiment on the analog discovery, or the analog discovery 2, for example, and see what is the smallest pulse that its logic analyzer will detect. But in this, I'm trying not to confuse the digital discovery with the analog discovery, so I'm not going to do that here. At any rate, I hope that this has been a sufficient review of the digital discovery for you to decide whether you want to own one and use one. I emphasize at the very end, this is a digital instrument. It's really intended for systems, for example, embedded processors. It is optimized for low voltage CMOS, in other words 3.3 volts, and it's a digital only system. So if those are the sorts of things you're looking for, then I can recommend the digital discovery. I think I'm going to recommend it for use in some graduate digital labs, and certainly for someone that is looking for a fairly capable, fairly high frequency, fairly wide bus option for displaying and analyzing digital signals. I think this is a very good value. So I hope you've enjoyed the videos. I will probably do some further work with the digital discovery, but at this point I'm going to call this review at an end and wish everyone a nice day.